Our next speaker is Professor Carlos Pérez Moreno. This will be the online lecture again. The title of the lecture is The Hardy Littlewood Maximal Function, Sharp New Estimates on Weighted Lorentz Spaces. Professor Moreno, you are welcome.
So this is the title of my lecture, and I want to thank the organizer. Please, can you pass the... Okay, so, but I don't know how to... Okay, so I will try to... Okay, so I will try. So then go to next. I want to thank to Alexei and Tatiana, to the rest of the organizer, for being so nice to me. And I hope I apologize for not being there, but I hope that in the near future I will be in Rostock. So this is based. Can you do next?
Yes, based on work with.
Mm-hmm. Yes, it's a great work on Natalia Comazzo, Javier Dondicochea, Ambrosi, and Pérez. So some of them are colleagues, some of them are postdocs, and some of them say PhD student. Can you do next? And it's based on work of Thomas Hitonen and Ezequiel Rela. So some of the ideas come back from previous work with these authors. So pass to the next. So the plan of the talk is the following. So I'm going to review some classical aspects of the theory, how to do maximal function, quantitative AP theory, then the quantitative mixed AP theory, and then I will pass to the main result in Lorentz spaces. But first, I will mention the classical theorem by Chang and from the early A. So and the recent result is related to AP infinity quantitative. Mixed AP infinity all spaces. I will try to give an idea of the proof, the main cases, and the last comment will be about strong maximal function. I think that we have results, but not fully sharp, as in the case of how do you do maximal function. Therefore, I'll review some other questions. So then the motivation. Are you in the motivation slide?
Yes, we see it.
Okay, so I'm thinking, okay, because so how the maximal function is the classical operator, define the supreme of average over Q. So we can put Q or compute balls, center balls, which is often used in the center case, and of course it's a classical operator that is really important it's the center object in analysis, but also many applications. For instance, the theorem is the proof with its own application of maximum function. Rationality, but combined with maximal function. The classical estimate is that the maximal function bound on LP for p greater than 1 up to infinity. Okay, and the case paper 1 is for the replacement, the weak type 1 estimate for the maximum. All this is well known. So, as I said, so it's important in many applications, particularly again, solvable inequality, Fokker inequality, this kind of estimate based on the properties of the maximum function. So the model example is of the weighted inequality is for the maximal function, is a weak type, but you have two weights, W on the left and MW on the right hand side. And from here, you can define the A1 condition, okay? The weight belongs to A1 if the maximum function of the weight is bounded by the weight, and with a constant C, which is greater, okay? So it follows immediately from this theorem. This theorem is to minus time from the early 70s, and it plays an important role in the area, because as a corollary, we have the corresponding LP result. So we have WMW P greater than 1, so the LP version. So actually, you can prove independently from the theorem, but it can be as a corollary of it, you can get the result as well, using interpolation theory. So why this is interesting is because of the vector value extension. So the maximum function has beautiful vector value extension that you can see in red. I hope you can see it. You know? So this is the sum of mj to the power q, so the little q inside and the great LP outside, and is bounded by the sum of the f in the little q space LP, big LP space. So this is a really nice and relevant result in the theory. So this is a part of the proof. There are several proofs, but the classical one is based on this weighted inequalities. And this shows how these weighted estimates are interesting. Here I'm using the notation with the LP infinity weighted notation that is here. And the strong. That's it's the usual one. I'm using the LP definition. So then let me just state the theorem of Marquez-Howe. So from the early 70s, the maximum function quantum weighted LP is found only the maximum function satisfy the correspondence of weak type, which is not usually in general case, but the case of maximum function it is so, and is equivalent to the AP condition. Okay, it's equivalent to the AP. Okay, as you know, this has been a very influential theorem. Okay, it has many applications over the estimate in concurrence over the many in the elliptic PD. So in many situations, the AP class of weights appear often. Okay. So this is what we call a qualitative result. So the boundedness is equivalent to saying that the weight satisfies the AP condition. But then in the early 90s, Buckley, PhD thesis was asked to find a better control, so a quantitative control between the LP norm, between the LP operator norm of the maximum function and the AP constant. And he found this result. I hope you can see that the operator norm of the maximum function is controlled by the AP constant raised to the power 1 over p minus 1. Okay, so this is the first result of this kind of analysis we do called quantitative analysis. So where it shows how is the operator is controlled by the AP constant. Observe that when p is 1, the exponent goes up. The AP constant is bigger than 1, so we can think whether there is a better exponent here in the 1 over p minus 1, but this is not the case. So we cannot replace 1 over p minus 1 by something smaller. Okay, like a 1 over p minus 1 set. So this is false. Okay. So this is a real result, and we have now like a different proof, but I will sketch one, by the way. But I'm going to show a better result. So what is called a mixed AP infinity estimate. So this, if you see this estimate, is difficult to say how to improve it. But we found the way to improve it, not by changing the exponent, by changing the constant AP. By changing the constant AP by a mixed one. AP constant, a little bit of the AP constant, and a little bit of the infinity constant of the dual weight. Let me show you this. So let's go to the slide that says infinity class of weight. Let me recall that is well known, the definition for infinity as a union of all APs. Okay, AP is an increasing class, so it's natural to define the infinity class as the union for AP. So, but it's not so easy to find a constant. So in the 80s was found a nice constant due to Khrushchev, the Russian mathematician, that he found a constant by means of the exponentials, okay, which is natural. When you let p go to infinity in the AP constant, you receive the infinity, the exponential infinity definition of the constant. It turns out that this constant is larger than this one, the one I'm showing you in front, the infinity constant using the maximum. So this condition was implicit in the work of the Japanese mathematician Fuji in the 90s. Also, Mike Wilson found a similar condition later. So we usually call it the Fuji-Wilson condition. or constant, even though it was never defined. So it's the integral over a cube of the maximum function acting on the weight localized to the cube divided by the measure of the cube. Okay, so if it's to see it, it's given one. Okay, so so an important observation using this constant is that we can give a reverse inequality, which is a key result in the theory, by using this A infinity constant. So you have a weight A infinity, will define this exponent 1 plus the inverse of infinity constant, essentially the inverse of infinity constant. With this parameter, you have the reverse inequality. And so the A value and norm of the weight is controlled by the average of the weight. The left-hand side, you have a gain. And you see in front of the constant is 2. This is important for application. The constant independent of the weight. Okay. So actually, we have something better. We have a better result. Instead of tau the infinity, we have tau n infinity minus 1. But let me just not care about it. So this is the result with Hamiltonian, and then we probably with Hamiltonian and Bell. So with this result, we can have what is called a quantitative open for AP class. So classical results say that the weighted AP then belongs to AP minus epsilon. So the AP cluster increases, so AP is containing AP when P less than Q, but it's open, so namely for the fixed weight that belongs to AP, a little epsilon, but the value belongs to AP minus epsilon. This is what's called open. So this is known from the 70s, so it was not long ago. But what we do know now is that the epsilon we have is controlled. It's controlled by this quantity, P minus 1 divided by essentially the infinity constant, or the one above, of W of the dual weight W, sigma, W equal raised to the power 1 minus B prime. Okay, this epsilon places a role in the new theory. So of course, the AP minus epsilon constant is controlled by the AP constants. You don't lose too much. Okay, let me just pass to the next slide. So improvement of Berkeley's theorem. So recall Berkeley's theorem. So the operator of the maximum function is controlled by the AP constant raised to the power 1 over B minus 1. So, but the new result that we have is that the operator of the maximum function is controlled by the AP constant raised to the power 1 over P times the infinity constant of sigma of the dual weight raised to the power 1 over P. And this result, one can show that it really improved Berkeley's theorem. Okay, so what we have on the right hand side is smaller than the AP constant raised to the power 1 over P minus 1. So, but at this point, when we are at this point, we don't know how to find the improvement. To tell you the truth is, I have no idea how to predict the result. What we know is that gives a result that we thought was true, namely the L2 norm, the maximum was comparable to the L2 constant, but indeed is false in this result. And let me not get into it. So this was first with Hamiltonian, and then we proved with Pérez. Okay. So the reverse held A2 conjecture is false, as I say, thanks to this thing. The reverse A2 conjecture was that the norm of the maximum function, the L norm of the maximum function, was comparable to the A2 constant. It turns out that it's false, thanks to this result. How to improve this theorem? I have no idea. Okay. What we have done is to replace AB by Lorenz's case. I will do that next. And before going to the Lorentz case, so let me give you quickly a sketch of the proof. So we are going to use the weak norm of the maximal function. So it's comparable, the weak norm, so the boundaries of the LQ into LQ infinity is comparable to the AQ constant raised to the power 1 over. This is somehow easy, using by the definition of the AP constant and the covered in yellow. So we look at we look at the LP estimate, we use the layer cake formula, and then we use the fact that the M is bounded on an infinity. So this is the trick of Maskiewicz. So we replace F by P. So where is F is big. So and then now we use the weak type property. Okay, the next step, the P, but we use the weak type property at level P, not at level P. We use the weak type property at level P minus epsilon. Why? Because the AP classes satisfy this open property, and we choose the epsilon that I defined before. Okay, so then by revising this by using Fubini, so we can write this integral in this way. The AP constant already, and then you see that the integral is an epsilon. This epsilon is the singular. Okay, so one of the one part on the AP minus epsilon operator. So it's essentially the infinity, the inverse of the infinity constant. And this is what here naturally the infinity constant in this estimate. So this is a proof of the AP and infinity, the mix, what we call the AP and infinity estimate for the maximal function. So let's try to imitate the corresponding result for the Lorentz space. So, but before let me recall what is the classical. So I am now in the Lorentz world, Can-Hahn-Cook theorem. So we have the weighted Lorentz space, okay? And I define this way. I don't use rearrangement. I use the distribution level set, which is somehow more, at least from my point of view, it's easy for me to think in this term rather than with the rearrangement. Actually, Can-Hahn-Cook use rearrangement, and I have to get I read many times I tried to read many times the proof and replace it with the good constant, and I was not able to do it. Maybe it's possible. Maybe you can do it, but I wasn't able to do it. But with this, using this distribution level set to the definition of the weighted Lorentz spaces, yes, we can. So the case Q equal P is the usual LP. The case Q equal to infinity is the usual weak LP space, Massenkiewicz space, sometimes called Massenkiewicz space. So the case Q equal 1 is especially on the theory because it's somehow the more singular one. And sometimes called really the Lorentz space, the case Q equal 1. Okay. So I pass to the next slide. So the Can-Hahn-Cook theorem. So this was done in the early 80s, 1982, and it was also motivated by Moreno. So this theorem says that if P is between 1 and infinity and Q is between 1 and infinity, including 1 and infinity, okay, so the maximal function is bounded on LPQ, and weighted LPQ spaces in the Lorentz spaces, if only the weight satisfies the AP condition. Okay, again, the AP condition is the one that governs this kind of question. Okay, so I'm using this terminology. This is a qualitative result, the qualitative result. So probably at the time nobody cared about the quantitative form. But what we do now is to understand the quantitative form of this result. Okay. So let me pass to the next slide, the modern version of the Can-Hahn-Cook theorem. So the idea is to get it, as before, a sort of AP infinity result, but optimal with one. So we assume P between 1 and infinity and Q between 0 and infinity, even. So if we can go below even 1. Okay, sigma is going to be the lower way as before. And the result that we obtain is that the AP constant, so the operator norm is controlled by the AP constant rated by 1 over P, is comes from the big type estimate exactly as the case equal Q in the LP state times the infinity constant of sigma raised to 1 over the minimum of P and Q. This is what makes a difference. So we have to choose the minimum of P and Q. When P is equal to Q, the minimum is simply P. Okay, and it's exactly the classical result, the result we obtain for the maxima in the LP case. So this is the novelty, to have the minimum of P and Q. And the result is sharp. So we cannot go belong, we cannot remove an epsilon in either of these parameters, neither this or the other one. So this is why we were happy with the result, but we realized that these exponents are really active. Also observe that P prime, the exponent P prime is optimized, one of the minimum P of the Q. I think this also P prime part is also optimized. What I want to do is sketch a little bit, not to give all the detail, just to sketch a bit. So we use the distribution level notation as usual. So I'm now in sketch of two. Okay, so in the slide called sketch of the two. So fix a non-negative function. Now we by the distribution of the function respect to the measure with the data measure. Okay, so we use this property. This is very easy to check, and we use the openness property. Okay, again, the epsilon comes from the epsilon that we divided is the singular part. Okay, is the inverse of the infinity part. So there are two cases: Q less than infinity. I will explain the case Q less than infinity. The case Q equal infinity plane is somehow the same, and probably it's more important for application the case Q of infinity. Okay. So schedule we use the layer 2 formula, and as before, we replace f by f sub e, so the argument of the mass and derivative, or at least this is what I think, and then use the weak type, the operator property. This is why I placed a by 18 exception first. Then we replace, so we just do some, we write what it is. This is nothing more than the definition, so this part is really not hard. Just we use the properties of the distribution function, okay, and we split it into the inner in there into. Observe that we have already the AP constant on the left. Okay, so we continue, and we are going to split it in two parts. So the first up to t minus epsilon, and the second starting from t minus epsilon. Okay, the first part is easy. The first part immediately gives you the LP norm. So this is the end of the proof. So this part is less singular than the second part. The second part is this, okay, and we're going to distinguish two cases: the case Q less than 15. So for this, we're going to use this estimate with the log, which is the log proof doesn't really play a role, but it's somehow easy to check. You've seen that the distribution function is decreasing, and then we use the Fubini afterwards, okay, and it's very easy to check this part. The case Q bigger than P is more interesting because we have to use Harmonic quality, okay, the classical Harmonic, okay, with wood bound, with one over epsilon bound. Then we obtain using Harmonic quality, we use the 1 over epsilon, and the 1 over epsilon is exactly the infinity quantity. So we put all these things together, and we end up with the result. Okay, so it's just a sketch, but I show you a little bit the difficult more. So I'm now in to the 5. So the optimality is at the very beginning we didn't know how to get the optimality. It turns out that it's a very easy example. So this is the weight, a particular weight for which the optimality is attained. So the delta P minus 1 in an interval, and then outside that interval a power weight. Okay, this result is plugged into the norm. So you get that the P constant is 1 over delta minus 1, and the optimality corresponds. So this is another proof. So let me just say a few things about the transmaximal function. The transmaximal function is exactly the average as before of the function, but instead of taking two factors. Okay? So this object was defined by Massinkevic, Sigmund, and Jessen in the 30s, a long time ago. And it turns out that there is an AP a class of functions for rectangle that plays an important role because it gives you the boundaries, characterizes the boundaries of strong mass function on weighted LP. Again, the classical LP theory. So but here it is the theory that I think is due to Back-Bien curves, although many authors say that maybe they knew the result, but appears in a paper that analyzes this result by Back-Bien curves. That the strong mass function bounded weighted LP if only is a weak type PP if only the weight belongs to the AP class with respect to rectangles. Okay, so let me pass to the more precise result. So the more precise result, quantitative theory is that the strong maximal function is controlled by the AP constant, the strong AP constant, the rectangular AP constant, raised to the power n over p minus 1. Okay, can you see the n over p minus 1, n in red? Can you see? So, and the weak type is the AP constant raised to the power 1 over p plus n minus 1 over p minus 1. These results follow, I mean, it's not immediate, but it's not hard to prove either, these results. And the important point is that it reflects more singularity, but we don't know whether this result is sharp. And it's a really interesting problem to show that n is sharp in either case. So, for instance, I think that one is the lowest one, the lowest exponent, because it's the case of a cubes. But between 1 and n, there is a whole world of parameters, and we don't know whether it's probably the most interesting problem in the theory, I mean, from my point of view. Okay, so why is that more difficult? Because the operators are not of type 1-1. They satisfy an N log L type modular estimate. So with S log L is minus 1, this is the case. When n is equal to 1, we are in one dimension, rectangles are interval, namely cubes, so everything coincides. But when you are in dimension higher than 1, is more difficult. So there is a reverse Held inequalities as in the cubic case, and there is a reverse property, which is this parameter, and there is an open property here. This was known a long time ago, but we now found the derivative is bound. So exactly the same with this new infinity constant. And with this information, we can have an estimate within the Lorentz context. So the LPQ norm of the strong maximal function is controlled by the novelty here is the log part. So let me put that we have the AP part raised to the power 1 over p plus n minus 1 over minus 1, as in the weak case, as the result in the weak case. And then we have the infinity constant raised to the power 1 over minimum t comma cube, exactly as in the cubic case. The novelty of the new object that appears here is the log of the AP constant raised to the power 1 over minimum p comma q. This is really intriguing. My feeling is it shouldn't be there, but it's probably our proof, which follows the line of the cubic case. Our proof is not optimal. So, and I think that the result is not optimal. I think we don't have any other example. So there are interesting things in the theory. So in the case n equal to 1, so you recover, you have the log in the case n equal. So this, to me, this is saying that the proof is not shouldn't be there. So, but we don't know. So thank you very much, and I'm sorry that for the drawing, and I would like to in the near future to visit you in person. Okay.
Let us thank the speaker. Do we have questions or comments? If this is not the case, then let us thank our speaker again.
Okay.